It is my pleasure to introduce 4 of the 10 or so current members of the PyPy project. PyPy is a hugely important open source project whose contents will be briefly presented today. It's been going on for 4 years. It's got more than 100 contributors in various proportions, but Samuele Pedroni, Armin Riegel, Laura Creighton, and Jacob Halen have as much title as anybody to be described as a core of the PyPy project, and so it will be it's a pleasure and an honor for me to introduce their talk.
Thank you. Thank you. Now we have to find out, can you hear me? Hello? Can you hear me? Can anybody hear me? Hello? Hello? Can people hear me now? Can you hear me now? People can hear me now. Good. Great. Great. Wonderful. PyPy is a tool chain for generating virtual machines. And it's powerful, it's amazing, but it started off somewhat smaller, as witnessed the name PyPy, which gets you the idea that it started off as an implementation of Python written in Python or anything else. And now it has grown. But the original history and motivations are fairly simple to understand. Dynamic languages, and Python in particular, are considered to be have problems in that there are trade-offs you have to make between speed, flexibility, and maintainability. And we know that Python isn't fast. So that's the compromise you have to make in the speed things. Now Python is actually fairly maintainable until you decide that it would be a good idea to start running on, say, the Java virtual machine. Or maybe you'd like it to run on .NET. Or maybe you'd like to do something like that. And then while the CPython implementation is still being maintained, from the point of view of the community, it's a much harder problem. And while this is of theoretical interest to some people, for the people in the PyPy project, it was of intense, burning personal interest. Over here we have Armin Riegel, who's the author of Psycho, which is a handwritten, just-in-time specializer for CPython. And every time CPython moved and there were changes to the language, Armin would have to do a whole lot of work to keep Psycho in order. And over there, sitting down, who's going to talk later, is Samuele Pedroni, and at the time the PyPy project started, he was maintainer of Judgment. And every time changes came by, he would have to hop all over the place to make things happen like that. And not here is one of the other founders of the project, and people who were there from the first days, Christian Tismer. He's produced a version of Python called Stackless Python, which has coroutines. It's basically a great big patch that you can apply to the C version of Python if you want this. And of course, when the language changed, he would hop around and have to make changes for this too. So while maintaining your own Python programs may be reason to say Python is maintainable, if you're actually maintaining Python from our point of view, it was a lot of work. And we'd like to do something about that. And the third thing that you have to give up on or make compromises with is flexibility. And we really didn't think that Python was flexible enough to suit us. And for flexible, we want to do things like plug in our own garbage collector and let's have a JIT, and let's go here, and let's go there, and let's go everywhere. And so what we sat down and decided that what we wanted was a Python that was fast, and a Python that was a whole lot easier to maintain, and a Python that was really, 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 really flexible. And these are rather ambitious goals, but that's what we wanted, and so we decided to do it. And after 2 years of working away at this, the European Union, who puts out academic calls and things like that for all sorts of scientific research, put out one, and we looked at it, and we found something that if you squinted and looked sideways, looked kind of like what we were doing. So we all decided that it would be a good idea to get paid to do this full time. So for 2 years, we have been and have just finished being a European Union 6th Framework IST computer science research project. So in addition, in addition to being from starting off as our own open source project like any other one that happens when a bunch of friends get together and say, let's do something, we ended up as a big, impressive, important research project. And now we're back to being an open source project, and that's about where the project ends today. So that's the history, and that's the motivation, and I think we'll go on to somebody else to give more slides. Teach me how to get it.
And I will talk to you about the architecture of PyPy. Architectural decisions are, because we have managed to accomplish a lot of our goals through the selection of good architecture. Start with the normal situation you have when you program in Python today. You have your program written in Python, which is submitted to the interpreter written in C. It takes as its input something written in Python. The program is written in C, and it has as its assumption a Python virtual machine and POSIX as its platform to run on. And then it does whatever you want the original program here to do. Next, please. One of these Python programs you can write is an interpreter for Python, which runs on top of the original C interpreter for Python. And that's what we've done. So we have an implementation of Python in Python. Of course, if you do an interpretation of a program on top of an interpretation of a program, this becomes extremely slow. So we're about 2,000 times slower than ordinary CPython when running this way. And this is, of course, not practical. However, what we do have is a fully testable, nicely implemented interpreter in a high-level language. And this is one of the great benefits here. But how do we regain speed? What we do is that we take this same interpreter and run it through a translation tool chain to produce an interpreter in C running on top of the POSIX environment. In order for this to work, we can't use the full Python because we're going to translate it into C, which is a statically typed language. So we must be able to do type inference on this program. So we have something called RPython, restricted or reduced Python, which is a limited subset of the full Python language, which we can do this translation on. And out of this, we then get an interpreter that takes a Python program just like the other Python programs and runs them. So this then becomes essentially a replacement for your C implementation of Python. If we focus on the translator, this takes a program written in RPython and translates it to C, and it in itself is implemented in Python. This is actually the big achievement of the project, because writing an interpreter for Python in Python is a relatively simple thing, while the translator toolchain, which yields the fast interpreter, is a lot more complicated. But when we do automatic translation in this way, what we can do is that we can have plugins which generate code for different backends. So instead of generating for C and the POSIX environment, we can, and we have done, an implementation for the Java virtual machine where we have Java bytecode, and the same thing for CLI and .NET. So from the same source code, we get code for different environments. So instead of having to make totally different implementations for Java, like Jython, and for .NET, like IronPython, we have the same source code to start with. And we can expand this to other platforms. We have done experiments with Smalltalk, Scheme, and you can imagine your own platform you can do this on. It is not a huge project to make one of these plugins. The translator, I said, was something that takes a program written in RPython and translates it to C or the Java virtual machine bytecode, etc. It's really general, so it can translate any interpreter written in RPython for whatever dynamic programming language you like. Run it through the tool chain and get an interpreter out the other end. Indeed, you can, if you want, take any program written in this reduced subset of Python, run it through the translator, and get a C program out the other end. This can be useful for producing a C extension module for Python, for instance. And there are some people who do that. But it is not the point of the PyPy project that people should be writing things in RPython. This is only a tool for implementing interpreters, really. So to sum this up, we have a tool, a translator, which allows us to take a number of different programming languages and run them through the translator and yield a version of the interpreter for that language on whatever platform you want. So we essentially get an n times n m matrix of different interpreters we can produce. Now, we will make a quick look inside the interpreter for the Python language, which has some interesting architectural features. We start with a program implemented in Python, and like other interpreters, we run that through a compiler and get bytecode out. And then we run this bytecode through a bytecode interpreter. And usually, in other implementations, this is done in one big monolithic piece of code. What we've done is that we've separated out the actual objects and the operations on the objects in an object space. So the bytecode interpreter here sees the object space and the operations on the objects as black boxes. It doesn't know what the objects contain. And then we have a clear API in here. This allows us to take this object space and exchange it with another one with a different behavior. And it also allows us to put in proxies for the object space, which add behavior or change behavior to the original object space over here. And this turns out to be really, really useful for the flexibility of the programming language. And Armin will now show you a demo of what we can do with this flexibility.
So this program here is a version of PyPy that was compiled into a big C executable. So what you get is basically something that looks and feels like a regular Python interpreter. I mean, it's hard to see the difference, basically. There is one essential difference that some of you have probably noticed. It's the prompt. You have 4 greater than sign instead of 3. Okay, in this case, there is another difference. This is a version of PyPy that was compiled with a proxy in this sense. So we have added a special capability, a special semantics at the language level, which allows you to manipulate objects that are computed lazily. It's exposed in this special module. And func is a function that means the lazy result of calling a function. So let's imagine that here I write a function that does some horribly complicated computation that is going to take ages, like x+1, right? But now, if this is going to take ages, and if I'm not sure that I'm going to need the result, I just want a result and pass it around, and then maybe someone will inspect it, then I can say x equal func f5, which works like the apply function, but doesn't really call it until it's necessary. So now I can do things like pass it around, get it back, okay? And only if I do any operation on y is the value computed. And by any operation, I mean really any operation. It is not something you could do in CPython, for example. If you ask for the type of y, you're not going to get an answer like, oh, I'm a lazy proxy object or whatever. No. The thing is really computed, and the answer is really an integer, a perfectly regular int object. So I'll let you imagine what kind of feature you could implement with this kind of thing. The point of this demo is also that to implement this lazy object capability, we only had to write one of these proxy object space. That's about 200 lines of code in total in a corner of PyPy. It's not a change everywhere in the source code as you would need in CPython. And another demo, which is maybe a bit more obscure unless you know already what tainting is, well, tainting. The idea is that you get some data from some untrusted source, and if you mark the data as tainted, then, well, you can do basic operation with it, but basically the tainted value cannot escape to unexpected places. For example, if the tainted data is untrusted input from a CGI form, then you don't want it to go to your SQL query before you have done checks on it. Or for example, it's a credit card number and you don't want it to end up in a log file by mistake or these kind of things. So in this case, I can do basic operation with x, but I cannot really inspect the value. And tainting propagates to any results like this. So I cannot inspect the value in any way. Unless I am in a specific position in the program where I know that I'm going to get one of these tainted value, and I know that here in my program, I agree to be here careful in just these few lines of code, instead of having to be careful in the whole program about what you do with the value. So where you want to be careful, you say untaint, and then you get the value. And the kind of cool things you can do, because it's Python, you can say this, so we know it's 0, okay, but we cannot inspect it. And then you can say this, no explosion, that would leak information. So then you can say this. Okay, well, what is V? And the point is that it explodes only at the point where you try to inspect it. And there are debugging ways to recover that it was really 0 division errors, but it doesn't leak information, basically. Okay, so this is also another proxy object space implemented in 200 lines of code. And the point of this is not, well, I don't know how useful exactly this set of features is. The point is more that you can go and design a set of features that's useful for you by extending this or by using something similar. So that's it for the demonstration about the flexibility we have in the interpreter itself. And now Jakob will continue on the architecture of PyPy.
We should also mention that we have other things we've done with object spaces, like transparent remote object invocation and transparent persistence. So now we take a look inside the translator. where we take an interpreter, like we saw before, with a compiler, a bytecode interpreter, and if we're doing the Python interpreter, we also have a flow object space. So we've replaced the normal object space with a specialized one in order to be able to do flow analysis. So we take the entire interpreter, we do flow analysis on it, and we generate a flow graph. This then goes through a step where we do type annotation. So we go through the entire flow graph and we deduct what types everything has. And this is why we have to write things in restricted Python rather than full Python, because full Python is too flexible for total type deduction. So out of this, we get a type annotated flow graph, which then goes through a step called the R-typer, which transforms the high-level types we have here into low-level types for the platform we are doing. So we have two different kinds of translation here. One which goes for a C-like environment, which we use in the C backend and the LLVM backend, and one which goes for object-oriented backends, like the JVM and .NET. And out from this, we get low-level flow graphs. We can do transformations to these low-level flow graphs as well. So the stackless transformation is one thing that we add at this point. And then we do two paths of code generation. We generate code for an interpreter using the plugin we've talked about before for whatever environment we've selected here. And we have another path, which is optional, where we generate a just-in-time compiler. We're not writing a just-in-time compiler, we're generating one from the interpreter we've written before. And we add a garbage collector, and this is a plugin framework, so we can select which garbage collector we add. And all this generates a PyPy interpreter with just-in-time optimizations for the platform you've selected in your backend generation. So now we go on to some more demonstrations.
So I have a couple of demos of versions of PyPy that have been compiled with special features, where the special features have been inserted during translation, essentially by modifying the low-level flow graphs of the interpreter itself. So basically, we add features to the interpreter by this regular transformation of the interpreter while it's being translated to C, in this case. So the first demo shows bouncing balls. So what this is really is you have, well, it's a Pygame, the usual C Python process running Pygame that runs a PyPy subprocess, and the PyPy subprocess computes the position and velocities of all the balls, and it does so. The PyPy subprocess is a stackless enabled PyPy subprocess, which means that it has coroutine support. So all the states of the bouncing balls is in one coroutine. And now I've stopped the bouncing balls, and what occurred is that this coroutine was serialized. So I get a file here. This is a pickle file in the Python sense. And the pickle file contains a serialized coroutine. So that means all the internal state, like the local variables and all this stuff, is saved in the pickle file. It's one line. I say I want to save this coroutine here. Now you imagine that I take this file, which is 5 kilobytes, and I put it, I don't know, send it over the internet or put it on a USB stick. So imagine a USB stick and say, there is my running program on this USB stick, frozen. Put it back in another machine, and on the other machine, I can restore it. And you get exactly the same state restored and you can continue from there. So it's a pickle that includes the ability to pickle running programs or parts of a running program. It's not a whole image. It would be larger than 5 kilobytes. It's only one specific coroutine. So you can imagine a program with many coroutines, and you send some of them around in a distributed way. And the pickle format is really not an image. It's completely portable. You could reload it on the PyPy compile for the JVM, for example, and continue running over there. Okay, next demo is another kind of transformation. This is a version of PyPy that is fully sandboxed. It's in the same sense as you would have an operating system level sandbox, which would prevent the Python interpreter from doing anything bad, like accessing files or consuming too much CPU or memory. This is exactly the same set of capabilities with no operating system support. We just compiled PyPy to a C executable, and in the C executable, all the things that could be dangerous, like calls to the open function of C, for example, all these calls have been replaced systematically with invoking some external controlling process. And the external controlling process can do whatever with the call, including denying or giving another answer. Well, basically, you get complete sandboxing and virtualization. Here, I cannot write any Python code that does anything bad to my machine. Here, it's completely impossible by construction. And additionally, I cannot inspect bad things. You see here, if you look at the last line, that it pretends to have only these two directories in slash, because it's a virtual file system that the outer controlling process is presenting to the sandbox process. And the blue and purple lines are debugging information printed by the controlling process so that we know what's going on. So this was a feature that was inserted. I mean, that's again on the order of 200 lines of code to get this result. Now imagine if you want to do the same thing in C Python, you have to go everywhere. And even if you go everywhere, you're not sure it's correct because, well, there are ways to seg40 C Python. Maybe an attacker can exploit this. This is safe, basically. So that's it for the demo. Now we'll let Samuele Pedroni. Sorry, yes. Last demo is the JIT generation demo. Here is a completely arbitrary and boring function doing nonsense stuff with integers. It runs on top of the normal C Python in about 0.93 seconds per iteration. And with a PyPy C with a JIT enabled, well, you get debugging output, but then it runs 0.014 seconds, which is about 60 times faster. So we have a JIT that works well if your examples look like this one. And basically, we're working on making it work well for any example. But a point I should note is that the JIT works completely correctly in all cases. If you do random stuff like this, sys get frame, f locals, and I want to get the value of x and print it or whatever, this works. You kill a bit the performance by doing this, but it works. This is an example where the Psycho just-in-time compiler would give you just a warning and an empty dictionary for f locals because it cannot do it. So.
Can you change the x.add method in the middle of the loop?
So, can we change?
Can you change the add method on x in the middle of the loop?
Yes, well, here x is an integer, so obviously I cannot. But if it were something else with a user-defined add, then yes. Basically, we get a just-in-time compiler that's correct by construction in our approach. And then we have to work a bit to make it really fast, but it's correct by construction at any point in time, which is a novel result in some way. And Samuele Pedroni is now going to explain a bit how we can get this kind of effect.
Is this working? Yes, now it is. Okay, what I'm going to talk about is indeed our main research result, and is indeed how we start from this forest of flow graph that the translation process produces, and how we generate a just-in-time compiler from that versus having to handwrite one. And the technique that we use are basically partial evaluation technique. There is a paper from the 70s that says it theoretically should be easy to take an interpreter and produce a compiler. The fact is, this is kind of hard, especially because what people have mostly tried to do is generating a static compiler. And the problem is that if your language is a dynamic language, usually you cannot produce a good static compiler, because the important thing when you try to improve the performance of a dynamic language is to be able to use runtime information and feed it back into this compiler. And to achieve that, you really need a dynamic compiler. Now the process that we use to generate our compiler is we start from the graphs of the interpreter, that is the intermediate representation that our translation toolchain uses, and we want to convert them into something that is able to do partial evaluation. It means some value are going to be known at compile time. One typical example for a dynamic language would be the bytecode, and we want something that would constant fold, in some sense, the interpreter, as given the bytecode as a constant. And the first things that we need to do to be able to do such a transformation is kind of to know for the value that flows in the interpreter, which one indeed are going to be compile time value versus which one are going to be runtime values. And this process is called binding time analysis in the partial evaluation technology, and will produce a coloring of the graphs. And to do this, we use our framework for doing type inference. And an important thing, we have this strange terminology we call the process of transforming the interpreter into a compiler, time shifting. Because in a normal interpreter, the interpreter runs at runtime, which is the time at which also the user program runs. And here instead we want to generate something that will compile ahead of time, the program that will then run at runtime. So about the coloring. The coloring, the point of the coloring is to achieve that we know we split the variable in the flow graph in such a way that we have green variables that are going to be compile time values, and we have red values that are going to be runtime values. And the process, all this process of generating the interpreter from the interpreter to a compiler needs to be driven by a few int. The implementer of the dynamic language need to add a few ints. And some of the ints are needed indeed to drive this process of find the colors. One of the things that we want to achieve here is, for example, to indeed mark the bytecode and the places where bytecode derived value flows into the interpreter as compile time value. So one of the typical ints would be to say that each single bytecode that we read out of the full bytecode sequence needs to be a compile time value. And from this int, we do basically a dependency sort of analysis, and we find out that the bytecode, the full sequence, needs to be compile time, and usually the program counter needs to be compile time too. Now, once we have achieved this coloring of our flow graphs, this induces a coloring on the operation too. We are going to have operations that are green, so the operands are green too, and the result is obviously green then. And this propagation is done when we indeed do the time p inference to find the colors. And then we are going to have red operation, which instead are operation on the red values. What will happen when we transform the interpreter into the compiler, we are going to get code in which basically the green value are going to be compile time values, so they are simply values. Instead, the red values are going to be runtime values, which means when we are going to run this generated compiler, we are going to use boxes that are sort of placeholder that will tell during the compilation process, this runtime value is going to live in this specific register or this position on the stack. But then what it means, what should happen with this operation in the graph when we do the transformation? Well, here we have a simple example. You should imagine that this f is one of these graphs inside the interpreter, and maybe even the eval loop, the graph of the eval loop function. And in this case, so we have an X that is green, that would be the bytecode, and a Y that is red, that would be the runtime value, for example, the argument to the bytecode that we are analyzing. And then here we have two operations. One is green, and one is red, and then we have an operation that mixes the two. Now the idea is that if we transform this interpreter into a compiler, the first operation is green, so it's going to be left unchanged by the transformation. The second operation, which is a multiplication, is going to be transformed in something that instead of being a multiplication is something that is going to emit a multiplication for the values that live in the position contained in the placeholder Y when we compile. Now it means that if you take the compiler that we produce from F, we will get this sort of result. And you should think of these two as assembler code or machine code. And in the case that our bytecode was 3, we will get this. The first operation is not there anymore at all because it's going to be executed at compile time and is folded. And so we get this 9 here and this 100 here. But instead, this 1 is going to appear again because the compiler contains, instead of this multiplication, the operation, please emit a multiplication. And this is about the operation in the graph. But one important aspect in the graph of the interpreter is the control flow of the graphs. And now we need to do something about that too in the transformation. And one aspect here, well, in the control flow graph, you're going to have decision point, like ifs. And now these ifs can be on green value, which are compile time value. This is not a problem. Such an if will just be left unchanged in the compiler because the value is known, so we know which path we need to follow. But if you have a decision point, an if on a red value, we are going to need to produce in the result of the compilation both paths, the true and the false paths. Now, as I said, the generated compiler has a state while it compiles, and the state is mostly the position we are in the compilation process, and all the value of the compile time value, and then all these boxes for the runtime values. And what we need to do if we have such an if is that we need to clone this state and schedule in a way both states such that we are going to compile both paths, both the true and false paths of the if. And then an important point is that the program has ifs, which are splits. There are two paths out of them, but then at some point the program flow will merge again. And at that point, we would like not to explode, because if you just continue and ignore the merging, we would just kind of exponentially produce a tree of code. So what we do is we have logic at merge point that we insert, which receives these various states that have been scheduled. And what it will do, it will use some kind of a unification logic to see, do I have already code that I have produced for this kind of state? And in that case, it will generate a jump in such a way that we can reuse code that we have already produced for a given compilation state. And it also means that we don't have this explosion. Now, an important point that I introduced when I started is that what I described so far would be good if our goal was to produce a static compiler. But we have a dynamic language, so the result would not be that good, because indeed we are not using any runtime information. So what we really want to be able here is to have some kind of primitives that allow us to feed back runtime information back into the compiler and really get a dynamic compiler that can use the fact that it is in a dynamic setting, and we have a running program from which we get values that we can use to produce better code that matches what's really happening at runtime. To do this, our technique, which is similar to technique uses more general, in more conventional dynamic compiler, for example, for the JVM, is that, and there this sort of thing are called polymorphic inline caches for people that know about them, is to generate some kind of open-ended switch that we can expand. And what we do in the places where we want to indeed have this effect of promotion from compile time to runtime, and this promotion need to be inserted as into people. The implementer of the language need to go in places. An obvious place is usually the dispatch logic in your dynamic language. That's usually the place where you have the runtime type of your object in the program, and you want to use this information to know what should I do next, which method is going to be called here. So that's a place in which the implementer of the language would put an int in which from one side, from the point of view of coloring, you would get this type, and the type is going to be red. And promotion, what it does, it produces a green value. Now when the compiler gets to such a point where such an int was placed, is going to produce this sort of expandable switch, and the first time around, stop there and just produce a default case that contains a call that is going to call back into the compiler with the value seen at runtime. Now to see something more concrete, here we have an f, which takes two values that are both runtime values, and we have such an int as I've described that takes one of these red values and produce a green value. This is a promotion here. And now, when we run the corresponding compiler to generate code that we want then to run, the first time is going to produce this kind of code. You should think this is going to be some kind of machine code. And so we get a switch on X and a default case that is going to call back into the compiler, feeding it the runtime value of X. Now if we run the thisproduce code, we start running it, and the compiler stops here because it has no idea what to do further, because it would really need to know this value at compile time. If you run it with 3, with X being 3, it's going to get here, fit this 3 back into the compiler, and then the compiler is able to continue because now this x1 is 3, and it can fold this multiplication and emit a multiplication for this 1. So it's going to add a case to the switch, which is the case for 3, and produce this 9 plus the multiplication of y and y. Now this shows some code that doesn't really exist in the Python interpreter of PyPy, but gives an idea of what kind of concrete situation you would use promotion. You should think these are two runtime values, and they are going to be box object in Python. For example, boxes for int values. And then what this code here, it implements indeed the addition for int values. If the type of both boxes is I'm an int box, I'm an int object class, then I can read out the value from the boxes, do the addition, and produce a new integer value. But now if we add what we can do here to improve performance when we create the compiler is indeed to put hints that will promote the runtime value, the runtime interpreter type of these boxes, which means that when the compiler generates code of this, it will first check, it will generate 2 of these open-ended switches, and then when it sees, for example, really 2 integer, it will add a case to both switches that check if these classes are going to be the int object class. And if it goes through both these cases, it will end up here, and then it's going to be able to simply emit one addition instruction. Now I'm going to show as an example in which, a practical example of this. Do you want to do the demo? Because well, Armin is going to do this part.
Okay. So well, we have a JIT generator that works when applied on the full PyPy language, but we have also written small toy languages in which we can try our JIT generator, of course. So this is one of the toy languages which looks completely unreadable. It's just a stack machine kind of thing. You push values and you do multiplications like here. So this is a factorial.
Yes.
And the toy language, the interpreter for this language looks like this. I may need to look around a bit.
JIT, TLC.
Here it is. So it manipulates boxed objects, which look like this. This is the abstract base class for boxed objects. You have a subclass, which is an integer box, which stores an integer value. And you see method. For example, here is the add method. How do you add myself as a box with another box? And there are other features not used in this factorial example, which are Lisp objects, which are count cell, nil object. So you have more bytecodes to manipulate this kind of stuff. The interpreter itself starts here, and you see, well, here is code which is a string of bytecode, which have been compiled in some way. Here code is just a string of bytecodes. You get the next bytecode, and you have if, elif, well, switches on the different bytecodes that exist. For example, addition is here. If you ignore these two lines, then you can see here, you can see here the addition. It pops two objects of the stack, calls the add method, and push back the result. But as Samuel described, with these two hints, when we turn this interpreter into a compiler, the compiler will generate code that checks and promotes the class of these two boxes. And the result of this...
You want to run the test or just go to the graphs? Yes. No, it's in IBM, I fear.
Sorry, bit of looking around. Okay, so if we now take the generated compiler and feed it the bytecode of the factorial function that I showed in the slide, it's going to generate assembler code. This is, well, you have to think about this as assembler code. Actually, we have several backends for our just-in-time compiler. It can generate assembler for x86, for PowerPC, or it can generate again this pseudo-assembler, which is what we use normally to debug and inspect stuff around. So here, the important point in this, well, you have to think that this is generated assembler. And in order to compute this factorial, it's first, this box here is the promotion point. This is saying I want to read the type of my, so I mean, the factorial gets an argument. So the argument is this V6026, which is a box. So I first read the type of the box. And for technical reasons, the type is cast to an int just because the switch, well, can only occur in an int. And this is a switch which has only a default case because we haven't generated any code for, I mean, we haven't seen any concrete value for the type of this box. And the default case contains here in the middle a call to the compiler. So the generated assembler code contains a code that goes back into the compiler and feeds this value here, which is the value I switched on. Feeds it into the compiler and then comes back to the switch. It looks like an infinite loop, but the trick is that the compiler is going to modify this switch to add cases when they are seen. So this is the initially generated code, and now if we really run this code by really passing it a concrete integer value, then compilation will continue, and it will generate an extra switch, an extra case, and we get this code. And we can see here above is the same as before, but now there is this extra case with this integer value. That's the integer value of the pointer in memory, basically the address in memory. And so this is all the generated code below here is the thing you get for the case where the input argument was really an integer box. And the first thing it does is unboxing, so reading the value, the integer value out of the box. And the interesting point is then, in all the rest of the generated code, now it was able to deduce that all the objects were integers. I mean, for the input argument, it had to check with this complicated switch mechanism here. But for all other objects manipulated by the bytecode, it could deduce that they were actually integer objects, boxes, because they were produced just now, just before, by the previous operation in the same function. So here we get, well, there is a bit an unrolling, but near the end, if I zoom out a bit, you can see this loop, which goes back up here and down all this way. And this loop now contains, there are a bit of checks to see if the loop is ended, but then essentially it contains only these two operations, an integer multiplication and an integer subtraction, as you would expect from a factorial. And this int mul and int sub, it's really the one assembler instruction that says multiply, subtract. So when you really compile this to assembler, you get really multiply, subtract, jump back, check if I'm at the end by this integer lower than, check if the counter is smaller than 1, basically, exit if it's so. So basically, you get excellent assembler code out of this. And everything is completely unboxed. All the allocation and reading back of all the integer objects that you would normally have if you were to interpret this factorial, all this was completely melted away. And there is only one boxing left here, which is at the exit, because the answer is an integer which escapes in some way. I mean, goes back into the outer world. So you have to really allocate it. So we get, well, that shows the techniques that we use. And we get the same kind of result with, for example, the F1 functions that I showed running on top of PyPy. And yes. That's why you get this kind of incredible speed-ups. You get good machine code and no boxing, so no memory allocation anymore.
I think we go back to the first slide and we take questions.
So that's it. This concludes this talk. And now I guess we can take questions.
And an important point is that the ints are introduced into the interpreter. Not the user program doesn't have ints. As we have seen, F1 was simply F1 without ints. The ints are for the language implementer to add to the interpreter.
Yes, so far we have added about, 10, 20 hints into the source code of PyPy, and that's it. It's not also like we need to add tons of hints everywhere. It's just a limited number. So the purpose is really that then it's possible to evolve this language, this Python language, to add new features to it. And we always have an up-to-date just-in-time compiler because there are very few hints to maintain.
Yes?
How does all this interact with debuggers?
The generated hint is correct by construction. We have a trick that we are using, an advanced feature basically, which is the Python frame objects. The Python frame objects have a complicated virtualization mechanism, which means that they are so far they are really allocated on the heap, but they are kept empty. And when debuggers try to inspect the Python frames, from code that is not necessarily jittered. I mean, the debugger itself is not jittered, obviously, typically. When you try to inspect the Python frame, it contains logic that can actually inspect the values from the C stack, that supports the running jittered code. So basically, we generate debugger-friendly kind of JITs out of the box.
PyPy tracking the tracking the CPython feature set.
So how closely is PyPy tracking the CPython feature set? Well, so far, the answer is that it's extremely easy to do so. And in practice, we have really, the last 2 years or so, focused on the translation toolchain, so we are still mostly at 2.4 versions with some 2.5 features because simply people showed up and wanted to add them. But basically, the point is that it's easy.
Okay. I suppose that's it. There is one.
This is a great research project. When's the plan to get to something that people can actually use real life?
So what is the plan to get to something that people can actually use in the wild? Well, I think we are almost there, basically. I mean, we have a Python interpreter. It's very complete. It's missing a few extension modules, but I mean, things like zlib and most of these standard C extension modules, we have some. So we need a bit more polishing, basically, but sometime next year we should be really usable. And for specialized use cases, we are already. I mean, if you're looking for a sandbox PyPy interpreter, just use it. It's here, it's safe, works. So I mean, we want to be more than just a research project from the start. That's clear. And all this is available. It's MIT license. You go and download it. It usually works.
How do extension modules work? Swig and things like that.
Well, right now our own extension module are written in our Python 2. We are starting to think to get a C types for PyPy. We have some way to our own way. We tried for a while to use the kind of C types definition to express how to link to C libraries. Now we have a slightly different way based on our own internal type system, these low-level types that we use in the graphs. And what we are thinking next is indeed to have some kind of C types at application level. And for large library like GUI toolkit, we will need to think more. Because one aspect that we don't support right now is separate compilation. So all extension modules are compiled together with PyPy. At some point, we will need to start thinking about that, which is mostly, in some sense, fixing the API of the object space such that it has well-known name for the external module to link with, but also in terms that they have well-known name in the generated C. And once we have that, I think we could go to tools like Swig and change them in ways that you can get extension for PyPy too. There are also some very, well, not concrete ideas of maybe emulating the CPython API in some cases, but we are not sure we want to go there because there are performance trade-offs. You may get some extension working, but with a speed that you would not like, so there is not much point into that. But that's the situation about extensions right now. Okay.
Well, then we'll talk to them.